So we were, computing central tendencies of, some standard distribution and density functions. So the next is, the Poisson distribution. So, the Poisson distribution is represented in this manner. I mean, the significance of Poisson distribution is, it's when the probability of success is too low, we use a Poisson distribution. When the probability of success is really low and the number of trials are very extremely large, right? So, there is some natural correspondence between a geometric and a Poisson distribution. It comes from the same Bernoulli family. Okay, the way it is that, you write it as in the following manner. Okay. All right. Okay. So the expectation of the Poisson distribution is just the sum. It's an infinite sum, right? Okay, because you have to do the expectation, experiment multiple times. So this is what it is. Okay, and this is nothing but the mu, the mean, right? Okay, so what we do is this. Since e to the power minus alpha is constant, right? It has no bearing on the summation. You can pull this out, right? You can pull this out and you can rewrite this thing as 1 minus k minus 1 factorial alpha to the power k. Okay, all right. So far so good. Now what you can do is you can change the index of summation from k to m is equal to 0 to infinity, right? Okay, 1 over m factorial alpha to the power m plus 1. Okay, so this is simply, replacing k minus 1 with m. It will have no bearing on the summation, right? Okay, it will have no bearing on the summation. However, what we should do is, what we can do is, because the first term is really 0. Okay, it's like, so you can change the summation here. Okay, because the first term is really, when you look at it, you change the summation here. Okay, all right. So now what happens is, let's see whether this can be, simplified further. How do we do that? Is that once again, this alpha to the power m minus 1, I can write it as alpha to the power m times alpha, right? And since this alpha is constant, just pull this out. Okay, so this is alpha e to the power alpha minus alpha, and then I have the summation m is equal to 0 to infinity alpha to the power m over m factorial. Okay, do I know what this is? I bet you do, right? This is the power series expansion of the exponential function. So this whole thing is e to the power alpha. So you have e to the power alpha cancels out and you have just alpha. Okay, so for a Poisson distribution, the mean just depends on the parameter, on the average. Okay, all right. What about the variance? The variance is, okay, according to definition, this is what the variance is. Okay, so once again, the standard drill, you pull this out and you have k times k. You can write k square as k times k, right? Alpha to the power k over k factorial. Okay, excuse me. And then you can rewrite this as e to the power minus alpha and then adjust one k, and so this is still k, alpha to the power k divided by k minus 1 factorial. Okay, well, it's when it's k minus 1 factorial, you have to change the index on k, right? Because otherwise it makes no sense. And so this is what you sort of have, right? Now what we try to do is, we just like previous step, we replace k minus 1 equal to m. So that means k equal to m plus 1. This will have an effect on the summation inside. So I'm just going to work on this particular summation, and I've just ignored the constant multiple that lies outside. So what will happen is I'll have this, when k is equal to 1, m equal to 0, when k is equal to infinity. So these summations will change from m equal to 0 to infinity, right? And k is m plus 1, right? Alpha to the power m plus 1 divided by m factorial, I think, right? Okay. Now what can be done is I can split up the sum, and I can rewrite this in the following manner. So which is m by m factorial, which is 1 over m minus 1 factorial alpha to the power m plus 1, right? And then the other sum is m equal to 0 to infinity alpha to the power m plus 1 over m factorial. Okay. Now from the second term, what I can see immediately is that I can write this as alpha to the power m times alpha, and this alpha I can pull out. Okay, so this can be written as alpha times this. Okay, all right. Now do I know what this is? Yes, I do. So this is nothing but e to the power alpha. This is the power series expansion, correct? So this is e to the power alpha. So I am at peace with the second expression. I have no problem with the second expression, right? The first expression is what I should, work on. Now, however, what you should realize is that the moment the denominator is m minus 1, you have to change your index. Okay, and you have to change your index, and you can also bring out, this alpha here. Okay, all right. So if you do that, I'll have this alpha to the power m over m minus 1 factorial, right? Okay, and probably what I should do is I will pull out another alpha. Okay, so alpha to the power m can be written as alpha times alpha to the power m minus 1, and then pull this out as well. Okay, so therefore, if you do that, you'll have, instead of alpha, you have alpha square. Okay, and here you have alpha to the power m minus 1 over m minus 1 factorial, m equal to 1 to infinity. Perfect, right? So this is the same power series expansion, right? And this will also result in e to the power alpha. Okay, so what I'll have here is alpha square e to the power alpha plus alpha e to the power alpha. Okay, all right. So okay, so this is just the but however, what I did not realize is that I was just working on the inside summation, right? You do have an e to the power minus alpha, which you did not account for. So now when you are combining everything, your final expression is nothing but, e to the power minus alpha, alpha square plus alpha, e to the power alpha. It cancels out, and you are left with alpha square plus alpha. However, we are not done yet, because the variance is not only this. The variance is this. The variance of x is e of x square minus e of x. Okay. So we have only computed this part, e of x square, which is alpha square plus alpha. However, we already know what is e of x, right? This is e of x, and which is alpha, right? So minus alpha square. So the variance is also turns out to be alpha. So the mean and the variance both turn out to be alpha. Okay. Okay. So this is as far, since we talked about, we talked about two discrete density functions, distributions, we should now, because we have applied Gaussians, we have used Gaussians in so many different places, and including Bayesian, regression, that I think it's a good time to, talk about continuous random variable, okay, which is a Gaussian density. Well, a Gaussian density is public knowledge, right? E to the power minus, okay, all right. So the expectation or mu is the integral this, okay, all right. Now what this implies is that I do have the function in itself, and this is constant. I can pull this out, so probably this should not bother me much. I can just write the variance just outside the square root, and inside the integral is just minus infinity to plus infinity x e to the power, okay. Now what at this point of time, what we should really be doing is sort of try to figure out how we can simplify this, okay, all right. So probably one thing that can be done is the z normalization, which is this, okay. Now if you do that, you know that your dz is dx, right, and x minus mu by sigma is z, so this is this thing will be z squared by 2, and the limits of integration will not change, it will remain the same, right, okay. So I mean I can rewrite this. This will actually be far more simplified than anything else, right. So x is going to be this, right, so mu plus sigma z e to the power minus 1 by 2, x minus mu square by sigma square can be replaced as c square, and dx as dc, okay. And of course I have this constant multiple which will be carried forward, but I mean this is far simpler to handle, right. I mean then I can simplify this further by splitting this up, okay. And while splitting this up, I am just not carrying forward the constant multiple on the outside of the integral, right, okay. So I'm just writing this as mu e to the power minus z square by 2, and then this is sigma z e to the power minus z square by 2, okay, okay. Now the second integral I should not be bothered much. The second integral should not be bothered much, because the second integral, when you compute, you can see, I mean this function is an even function, okay. I mean it's symmetric, and this is odd, right. So you multiply z, an odd function, with an even function, you get an odd function. An odd function computed within symmetric intervals of limits of integration will actually give you 0. So this whole thing will go to 0. I don't really have to worry about this at all, right. So all I'm left with is this part, okay. So finally the computing the expectation boils down to computing this is out, okay. I mean we are not done yet. I mean this is actually known as, this is also very famously known as the Gaussian error function, but simply ERF of Z. Okay, all right. However, we need to be still able to compute this, and so let's do that. So probably at this point of time, I can just, simply erase everything else and just keep this expression and try to, work on this particular expression. Okay. Okay. So let's, we'll do that. Is there anything that you see in the structure of the function, I mean the integrand inside the integral, right? Okay. That will, sort of help us in any way, anything that you observe. Except the fact that it's a symmetric function, right? It's an even function. Okay. What we can do is, let's, think of this as some integral I. Okay. All right. So I'm going to do this. I'm going to, represent this as an integral. Okay. In fact, I'm going to represent the square of this integral. So just take the square. Okay. If I do that, right? So far so good. Yeah. Okay. Now the square on the right hand side can be written as the product of the integral with itself, right? So what I'll do is, it sort of sounds juvenile, right? But this is a necessary action. And the next thing is, because z is a dummy variable, right? In one integral I can keep z, in the other integral I can change z to y, and nothing will change because these are just representational variables, right? So let's do that. So it's minus infinity to plus infinity e to the power minus z square by 2 dz minus infinity to plus infinity e to the power minus y square by 2 dy, right? Okay. And the reason for doing that is because these two integrals, since these are between the same limits of integration, can now be combined. These two single integrals can now be combined into a double integral. Okay. So we can do that now. So this is minus infinity to plus infinity e to the power minus y square by 2 e to the power minus z square by 2. Now it becomes a double integral, right? dy dz. Okay. All right. So, just for the sake of, saving some space, I'll just corner this down because this is my ultimate objective. So this is mu over square root of 2 pi sigma times I. This is what we want to compute. And so therefore I'll get rid of this. Okay. And what I'm doing right now, I'm just computing the I. Okay. Then the next step is I can just combine these two and I can write this as minus y square plus z square by 2. No problem, right? It's a simple algebra. And then the next step, what I intend to do is that, I change these to polar coordinates. Just, not for fun, because the structure y square plus z square is kind of attractive. So because if I do that, what I can immediately see is that y square plus z square is nothing but r square. Okay. All right. And dy dz would be r dr d theta. Okay. And tan theta will be equal to y over z. Okay. And the limits of integration will also change accordingly. I think what will happen is when both y and z approach minus infinity or plus infinity, r will approach from 0 to infinity, right? Okay. All right. And r will approach from 0 to plus infinity, and theta, because y and z are both approaching minus infinity to plus infinity, so tangent of theta is equal to y over z, so it will be 0 to pi. Okay. All right. So your integrals and the limits of integration have been changed from Cartesian to polar, and what you are doing now, it's e to the power minus r square by 2 r dr, and you just have a d theta. Okay. So now this is becomes much simpler to handle compared to a Cartesian, right? So now we can actually go back to two single integrals and just deal with each one of these separately. Okay. So e to the power minus r square by 2 r dr, and then it 0 to pi over 2 d theta. This is simple. This is just pi over 2. No problem, right? What about this one? This will be, when you integrate this, this is simple to integrate, right? I mean, so if you integrate this and you apply the limits of integration, you actually get 1. Okay, so what you see is now is this is the value of, I. So 1 times pi over 2. So rather, I mean, I think what you should get here is, sorry, you have a 2. So 2 and pi, so you have a pi. So this is what you are going to get, right? Okay. So this is mu over square root of 2 pi sigma times I. I square is pi. So what is I is square root of pi. So it'll cancel out. Okay. Alright. And you will have in your expectation, in fact, there is a sigma. I think I missed somewhere. Probably I won't have this, right? So this is just me. Okay. So this is the central tendency of a Gaussian density. Okay. All right. And this is what we expect. We actually compute that. We find that, when you do the MLE as well. Okay. All right. So that's about it.